So, next thing I like to go to is, I like to give the example. I like to show, so if there's two plates, and they're conducting, they're neutral, they have no charge, and they're really close together, and they're in a vacuum. So do you guys know what a vacuum is? So it's just, does anybody? Not you. Okay, so all a vacuum means is it is just the absence of particles or absence of energy. So there's nothing in the vacuum. So there's nothing around, like nothing's possible happening here. So classically, the energy will just be zero. Nothing happens. So what would happen to these two plates that are neutral, so according to Maxwell's equations, they don't experience a force? What happens to them?
Nothing.
Nothing. Cool. So that's what we think. That's what, if you're at the toddler when you were examining the universe, you would say that nothing happened. So what actually happens is these plates attract each other. And that is because the plates are in such a small region, so they're so close together that the laws of quantum mechanics. So you have to take quantum mechanics into account now. And one of the uncertainty principles is a change in energy is a change of time. So you can't be certain what your energy is time. So for a small amount of time, energy just pops into this vacuum. So it perturbs the vacuum. So we have a vacuum with no particles, but because we're so close, because we're looking at a scale so close, what happens is energy just pops into existence. And they are taking the form of virtual particles. So we have virtual particles popping in and out of existence in this vacuum on the inside and the outside. And because of this boundary condition, the number of possible virtual particles could exist is higher on the outside than on the inside. So it causes a pressure and pushes the plates together. So yeah, so this still, the more, you could just think about it as much as you want. Doesn't really make sense, but what will help is to have some mathematical background to it. So this is where I like to get into quantum field theory. And this is a result of quantum field theory. This is the experiment has been done. This is true. It rains legit. So we this whole time. So what's the field? So if you close your eyes and you picture a field, what comes to mind? You say the first thing that comes to mind when you picture a field.
A limitation.
A limitation.
Like a boundary.
Boundary. Okay.
Energy.
Cool. How about like a field of grass?
Oh, a field, like.
Yeah. So we're saying the universe the universe has no boundary. It's infinitely big. So let's just say this field of grass is infinitely big. So at every point of this field of grass, there is a blade. So every point there's a blade of grass. So in a field, let's just say the electromagnetic field, there is, at every point we could just say, or just like a field of photons. So every point we could just say there's a photon at that field, or a particle at this field. So physically, just like how there's a blade of grass at every point, we say there's a particle. And because it's quantum mechanical, we saw that particles could behave like waves, and we represent them with the quantum harmonic oscillator. So at every point, see, this is just for one. So we just went over the mechanics for one harmonic oscillator. So at every point, there's a harmonic oscillator. So you just put a harmonic oscillator at every point in space. It has its own, mathematical realm which it lives in, called the Hilbert space. So each point has its own formalism for quantum mechanics. So just like how we saw in here, we could say that we could construct a field now with infinitely many harmonic oscillators. So we could say this is point 1, point 2, particle 1, particle 2, particle 3, particle 4, and so on and so forth. Is this clear to everybody?
I have
Yep.
a question. So you say it's a vacuum.
Yeah.
So then, why we can say there is a particle? You're saying like the particle generated from the vacuum?
Yeah, so there's virtual particles.
Virtual particle.
So there's particles that could only exist for a short amount of time then disappear.
Okay. Alright.
So they're just packets of energy. So in this case, you could just say they're photons. So like photons that aren't real, like that only exist for a temporary time due to quantum uncertainty, pop into existence. So right now, also there'd be zero particles in this field. We don't consider virtual particles as real particles. They're just pretty much manifestations of the uncertainty principle. So we have different particles. So we could say this is our field where we have different particles, where we have an infinite number of particles. And we could do like the same thing for here, like the number of states. We could say this particle has energy 2, this particle has energy 0, this particle has energy 2, this particle has energy 3, yada yada yada. Or we could say instead of formulating our field this way, and because at the end of the day, all this does, all this quantity is just giving us the energy of this field by looking at each particle and taking its energy. So equivalently, we could just say that instead of these numbers representing particles, we just say it represents momentum states. So the particle, this one represents a momentum state 0, this represents a momentum state 1, this represents a momentum state 2. And the number that we put in here, rather than energy level, we just put the number of particles in that momentum state. So for this field, there's 1 particle in momentum state 0, there's 0 particles in momentum state 1, there are 2 particles in momentum that have energy 2. There 2 as in this h bar, so E equals 5 over 2 h bar. So there's 0 particles with this energy, 2 particles with this energy, 1 particle with energy 3, and we could do this for infinitely many particles. So is everyone following along? Okay, cool. So just like how
many particles, some of those numbers could be infinite.
So, well, yeah, okay. If you have, yeah, sure, because an infinite number, we could have an infinite number of particles, which, yeah, you'll see. So, yeah, that's correct. So so this is field, so this is position. So we look at the particle, and this is momentum. So now we could apply these same raising and lowering operators, but we just extend it to the field. So, and these raising and lowering operators, what they did was they raise and lower the energy. But in this context, what they do is they create and annihilate a particle in the field now, because we're dealing with energies of the field. So they create a particle, they annihilate a particle at a specific momentum state. So for example, and we could label it by a subscript. So I said 0, so it's A0, and the dagger means create. So what we get is we get 2. So now we have 2 particles because we created a particle with this momentum. So we have 2 particles. We still have 0 particles. 2, 1. So now if I annihilate so now I'm going to say still define this as an annihilation operator. And I have particle 3 on this state. What will be the new field? What will be my new field configuration?
1020.
1020. So my bad. Yeah, okay, yeah, sure. 10, yeah, so 1020. Yep. So that's right. 1020. Correct. Okay, so does anybody know? Are you confused? You're a little bit confused here.
But it's alright.
You're so no, it's not. You're so what?
We left off the normalization terms, right?
Oh yeah. So there are normalization terms. It's a factor of 2 pi. Yeah, just 2 pi, I think it's square root of 2 times the energy of that specific momentum state, if that's correct. Is that correct? I wrote it down here, yeah. Oh, it's just 2 EP, yeah. That's normal, like, yeah, let's not deal with normalization now. Like, that's just, I included normalization just to show you how we obtain the number operator. You know, so that was my purpose for including the normal, that was just to show. Yeah, we can leave off normalization for now. It'll come up when we start doing calculations later on in the course, when we start, deriving things, when we start, looking at, because from here, for like mathematically speaking, we just Fourier transform to get from position to momentum.
Fourier transform?
Fourier.
Fourier?
Fourier.
Oh, okay, sorry.
Yeah, my bad. Okay, so now we're going to take this state. So let's do so what do we get? Zero. Correct? Zero. Is that right? So now, like, what is this? If these numbers represent particles, number of particles, well, what's this?
There's no particles.
Yeah. So it's a vacuum. So we got back the vacuum. And remember from over here, each of these slots, if you like to say, has energy 1/2 h bar omega. So there's infinitely many slots with 1/2 h bar omega. 1/2 h bar omega. So we're gonna add all of them up, and then what are we gonna get? If we add, no, it's okay. So yeah, so classically we would get 0, but we're dealing with quantum mechanics. So this is like, so you have to like shift the way you'd like to think about quantum mechanics. So you're pouting. Is there something you'd like to say?
No, sorry.
Okay, yeah, that's cool. So yeah, so pretty much all of this, is just to, you're from the start, just to get rid of the notion of quantum mechanics. So anyway, so we're running out of time. So this is actually infinity because if we keep on adding terms, yeah, it's cool. So we're gonna keep on adding terms. We're gonna
Sorry,
say,
I got confused.
yeah.
What does a state means? That state means the number of particles in each
Yes.
energy level.
Yeah.
So then, why can we get the energy from? So it says that there is no particle. Does it have energy?
So it's because of this quantum. So even here, like there's,
Here and the state of 0 means
Yeah.
there is a one particle,
Yeah.
and that has the lowest energy level.
Yeah, but if this part, why can't the particle not be moving?
Yeah. But there is a particle.
Yes.
So then,
So even if there's so we're dealing, so this is kind of like the transition. So from here, we're dealing with particles, and here we're just dealing with energy, because there's no real particles in this vacuum now. So there's no, in this field, so we start off with a field with some real particles, and we got back. So we took away all the real particles, and now we're left with virtual particles. So I should just say, we took away from all the real particles, so the energy of this field should be 0, but because of quantum mechanical uncertainty, just like how the energy of this particle should be 0, the energy of this field should have been 0, but because of the uncertainty principle, we create virtual particles that carry energy 1/2 h bar omega in each possible momentum. So now we have these plates. So now going back to these plates, so we have one momentum with pretty much virtual particle with this momentum. We have a virtual particle with this momentum. virtual particle with this momentum. So is there anything unclear? So in this, so if we have a box, we have one real particle going with one momentum. We have two particles, both with 3 momentum, and then we have these still, because of the absence of this particle, there's still some quantum mechanical uncertainty happening that's causing virtual particles to exist in these momentums.
So zero doesn't mean nothing. I mean, so the zero doesn't mean absence of the particle.
Yes. So there's no real particle. So right now this is a box with 3 particles.
Okay.
Nothing doesn't exist.
Nothing doesn't exist. Pretty much, yeah. Yeah, sure.
Yeah.
Sure. So right now we have a box with 3 real particles, but then we also have an infinite number of possible momentum, which gets experienced due to quantum mechanical uncertainties through only for a short amount of time. So it's like, barely applicable. This is, negative energy. There's lots of things that come out of it. Well, yeah, so pretty much, there's a lot of things I want to talk about, but so when we talk about particles, we say they're points. Correct. Okay, so when we deal with points, what happens, I'll finish this off, my bad. So even though there's an infinite number of particles, an infinite number of possible momentum states that could be in the outside and the inside, because of this boundary, it restricts. So there's a smaller number of infinite possible momentum states in between the boundaries and on the outside. So therefore, there's an infinite number of particles that could pop into existence here, infinite. But however, because this boundary is restricting the momentum states, there is less particles on the inside than on the outside.
Can you repeat that?
So there are less number of particles, or less, because we're dealing with momentum states here, and because there's a boundary, there's a restriction on the momentum that we could have. So there are more, and since this is unbounded from this side, there are more possible momentum that particles could have on the outside of the boundary than on the inside.
But it's still infinite for both?
Yes.
There's just less infinite number
Yes.
between the boundaries?
Yes. So I don't want to make any mathematically incorrect statements, but if we have 1, 2, 3, 4, so so we have these are the integers, and then so if we consider that, or we can consider like the negative numbers 2, 3, so 0. So positive numbers and then positive and negative numbers. So there's an infinite amount of positive numbers and there's an infinite amount of positive and negative numbers, but because there's this. Well, then you have to deal with like cardinality, and like they might be the same. The cardinality might be the same. So yeah, I'm not too. I've been focusing.
Set of allowed frequencies for one is countable, the other is not.
Yeah. So, repeat that.
I mean, you have a discrete number of periods for your waves inside, right?
Yes.
So it's
So it's countable. Yeah,
The
exactly.
ones on the outside, I don't know if it
Yep,
really applies, I
it's-
don't know how mathematically it works for this, but yeah, outside,
Yeah.
you can have any frequency, that's not
Exactly,
countable.
yeah. Straight up perfect, yeah. I'm just like that, yeah. I took a proofs class one time. So we have 10 minutes, so what I want to get at is, in quantum field theory, so, we have these diagrams where like we say like particles interact with each other. So one, we don't deal with forces anymore. Forces are not fundamental, fields are what's fundamental now. Forces we're okay for, understanding physics at the level of introductory or in a college level. But we deal with fields. So we have an electron, we have 2 electrons interacting, and they exchange a photon and they come back out. We could represent this process, this is called a Feynman diagram, and we could represent it with a probability amplitude that this will happen, that this scattering, this experiment will happen. So they'll exchange a virtual particle. Now, because we're dealing with so now we're considering these to be infinite points. What happens is there's infinities that arise, and there's a questionable procedure called renormalization that we take account to deal with these infinities. Normalization. Sure. So there's 4 forces of nature. Could anyone tell me them? Does anyone know the 4 forces? Here, physics grad students. So there's the E&M, the electricity and magnetism force, which deals with, like what it says, electricity and magnetism. There is the weak force, which deals with particle decays. The strong force is which deals with holding, so the formation of composite particles, so such as a proton, that's made out of smaller particles called quarks, and those particles are held together by a strong force. And there's gravity, which, yeah.
And the dark energy now.
Is gravity. Sure, okay. That's a good point. So there's some dark energy which, maybe has to do with the Casimir effect. Oh, this is called a Casimir effect, by the way. Which maybe has to do with this situation going on here. But anyway, so you could renormalize these forces. But you can't renormalize gravity. So you could construct quantum fields from these forces, but you can't construct a quantum field for gravity. Because according to Einstein, gravity is just curvature in space-time. So here we deal with a flat metric. So that's just, our unit, so 0, 0. And this is, so the quantum field theory abides by this metric. And really all this is saying is if you draw a triangle in this space, the sum of the angles will equal 180. So A, B, C, A plus B plus C. However, Einstein said that the space that we live in is not flat, but it's curved on a larger scale, and that is what produces gravity. So that's what gravity is, just curved. So things go in straight lines, but like the GPS orbiting the Earth. So it goes in a straight line, but because the space is curved, it orbits the Earth, or such as the Earth orbiting the Sun. And when we have this curvature, so there's like a metric, I don't want to, it's like some potential, plus 1 plus some potential over 1, and then yada yada. So this deals with the gravitational potential. And when you take, so if you have the Earth and you draw a triangle, if you draw a large enough triangle on the Earth, you could actually make right angles out of these you could you could draw a right angle if your lines are big enough. You could draw right angles, and then each of these angles could be a right angle. So 90 plus 9 is 180, plus 9 is 270. So your sum of your triangle is 270 degrees. So this is a completely different mathematical framework than what we're used to dealing with, which we could talk about that later. But anyways, you can't construct a quantum field theory for gravity. So, and like I said, the issue that arises when these infinities that this process of renormalization takes account in is because these particles